Do you face power factor issues and harmonic penalty in your industry? Let us revisit your plant electrical distribution network and address how these harmonics can be mitigated from the plant user's point of view. Let us go in depth. So, revisiting to the plant electrical distribution diagram, let us say you have a mixture of 50% linear and non-linear loads and they are running daily. And years back, as per the EB norms, you installed around 40% of the capacitors, kVA capacitors of your demand, and say you have 1000 kVA sanction demand and you are recording around 900 kVA now. So, you first installed in your plant plain capacitors of 200 kVA at the SSB and 400 kVA at the powerhouse. You do not have a detuned reactor coupled capacitor banks in SSB and APFC also you do not have in the EB powerhouse. But you are trying to maintain the unity power factor, and this always leads to and often leads to leading power factor or unity above unity power factor, and it increases your harmonic distortion at the EB incoming. So, at the leading PF region your capacitors also act as a load and consume more kilowatt further. So, you are facing harmonic distortion penalty from EB, assuming we are talking about KWH building state is considered here. Let us go by the industry loading pattern first. See, your industry is having a steady load or a varying load or a dynamically varying load. This decides what type of harmonic mitigation you need to deploy in your industry. Either it can be a passive or a hybrid or an active or a combo of all these filtrations. And you can see the THD level from 10 to 20%, above 20% and above 20% with third harmonics as well. And most of the industries have varying loads only, and load and compensation at the motor ends, non-VFD motors, and a APFC system, variable detuned harmonic suppression filter and APFC at the SSB and at the powerhouse will almost solve your harmonics problem. And if your process is dynamically varying loads, then you need an active harmonic filter, and that will only address your harmonic mitigation first. So, steps to reduce the harmonics in stages from the field to the powerhouse, and as well improve the power factor in stages from motor panel to the powerhouse. So, most of your plants have varying loads only. So, plan for load and PF compensation at all your linear and non-VFD motor ends at the motor control machine control panels. Next, plan for AC line reactance choke at VFD ends and a detuned reactor coupled capacitor RCC bank at SSB and 3CT based sized APFC controlling detuned RCC bank at powerhouse to maintain around 0.95 lagging PF power factor. When the load ends are having poor factor, to plan to gradually stage wise improve your power factor from the motor panel to the SSB to the EB side, as well reduce the harmonics in reduction in stages from the VFD to the SSB to the APFC at the powerhouse. After this homework, you measure the TSD at the incoming, at your EB incoming, and if it is still higher than the EB norms, then you need to call the power quality experts next and let us address the issue collectively. Now we understand why the load and compensation is required for all your 3-phase motors rated above 5 HP. When your motors in the plant are getting older, their kVA also goes up gradually, and most of the motors in the plant are 50 to 75% loading only. You can see from 5 HP to 100 HP motors, the loading from 50% to 75%, you can see the power factor around 0.5 to 0.7 or 0.75 only. So, this needs to be improved to power factor of lagging PF of around 0.9, then only the power factor improvement starts from the motor control panel. Have you inserted a MCB at the incoming of your PF compensating capacitor at the load and at the motor control panel? You can routinely switch on and off, and it's at the capacitor to check the kilowatt, kVA, kVR and power factor at the SSB power meter. Say it is a 50 HP motor, you can see the improved power factor correction. Around 15 kVR power factor capacitor has been installed on the motor control panel, and you can see the kilowatt also reduced and kVR demand reduced by almost 46%, and more than everything the kVA reduction is around 17%, and the power factor improved from 0.8 to 0.92, around 15% improvement. So your capacitors need to be checked routinely every month to assure that you are achieving the above parameters in each and every load and compensation capacitors of your motor control panels. The capacitor's working condition and its location for efficient functioning, you address that first. Capacitors always derate silently. We will not be able to know how and why they are getting derated, but they get derated silently. If the capacitor takes the rated current in amps, say let us say 25 kVR capacitor takes around 33 amps, it is okay. But if the same capacitor takes below the rated amps, it goes below and below, then it consumes the same power, but the output kVR drops, the compensation drops. The capacitor unbalanced input current in amps, that also consumes more of watts and the output is drastically less. So the capacitors derate faster in harmonic rich region environment, over voltage stress and higher ambient. So you need to have the exhaust fan in the APFC panels and near the capacitor wherever you have installed, the thermal protection need to be given for the capacitor that is installed in the panel. But for any SLD, single line diagram from the transformer to the motor circuit of your industry, the L and C, the inductance and capacitance to stay in each ladder step to act simultaneously. This only will definitely improve the power factor from load end to the power house and reduction of harmonics from the load end to the power house. A good quality VFD will give a lagging of around 0.95 power factor at any point of loading, motor loading, say from 1/3 loading to say around full loading, and maintain minimum THD. First you confirm this point in your VFD whether it is happening, and this is not happening, then you need to add on external AC reactor along with the VFD's internal DC link choke. You can see the table, comparison table of AC reactor and DC link choke. Without reactor it is almost 90% THD from the VFD and harmonics from the VFD, and with AC reactor and DC link choke you can see from 90% it drops to almost 30%. This is what we wanted you to confirm from your VFD end whether this is happening. So the first priority is to improve the power factor at the machine panel for all the non-VFD motors, and this is low cost and easy to install first. The next stage is to plan for AC line reactor at VFD. This is a high cost. This is need to be done if the power factor is dropping less than 0.8 or 0.7 and there is no reactor fitted to the VFD, then you will have a drop in power factor and the harmonics will be more also, around 70 to 90%. You need to take steps to address this at the VFD end. Harmonic compliant equipments in your network, you can see the symptom of branded VFD is to maintain around 0.95 lagging. Then when your main motor's VFD is maintaining around 0.95, then why do you need a further plain capacitor at its incoming SSB? So you don't need, you never add a plain capacitor upfront of in your SSB at the input of your VFD panel. The capacitor needs to be sized for each motor at around 90% of the no load kVA of the motor. Active harmonic filters are needed to reduce the harmonics at the plant incoming only and not to improve the power factor at power house for the sake of poor power factor motors at the field. This is a costly solution. Detuned panels are mandatory, especially in harmonic rich environment and industries. Without detuning, it is very much at risk, and with detuned panel, especially the APFC, reactor detuned and reactor coupled capacitor bank, APFC 3CT based APFC, this will definitely maintain the power factor and keep the harmonics also to the minimum possible required. Years back your industry installed all plain capacitor banks in powerhouse and SSB, almost let us say a decade or years back, many years back. In industry utility, the VFD is there in any one of the pump or compressor or blower. If you have 3 compressors, you may have a VFD and 1 compressor. But all the other non-VFD utility in compressor or pump or blowers, you can fit a plain capacitor at their non-VFD panels. This is a low cost instant solution. In non-VFD production machines also, PF capacitor at load end is a must. For example, the textile spinning mill, it's all having non-VFD motors like carding cylinder motor or simplex or TFO or ring frame or combos or carding WRS and humidification plant motors. Wherever the VFDs are not been fitted, there the load and capacitors need to be given. Then only you can see the stage wise improvement in power factor and the harmonics reduction can be seen accordingly. All these case studies have been discussed in the energy conservation books, and this can be purchased online, and it is available online, and all the articles are available in my LinkedIn posting also. So, sharing the knowledge to save our energy that is commonly available to us, and the energy education is half done in the energy conservation. Industry sticks to the unity power factor even now, assuming it is as per the EB norms, but it is not so. Harmonics monitoring and detection is the need of the hour now. The EB allowed the industry to maintain the unity power factor, and maintaining around unity power factor and above unity power factor is a loss only for the industry. Not only for the industry, it is for the EB also in case of non-linear loads in the industry and leading power factor situation at the EB incoming side. So, industry needs to be satisfied with lagging power factor of around say 0.95 instead of pumping TSD to the grid and above unity power factor and leading PF region, and many industries have already invited penalty due to this unstable conditions at above unity power factor region. Many of our energy audits, having done around thousands of energy audits in the industries and buildings, the many industries have reduced around 0.95 there and keeping a lagging power factor, and their TSD also reduced, and the nuisance strippings also avoided now. And the main point is the APFC that they are trying to maintain is 3CT based, and it needs to be fine tuned so that the PF band is not big, it is pinpointed, say around 0.95 or 0.96, it should be settling at that region of 0.96 to 95 like that. Then only you can achieve less amount of harmonics from the industry and PF improvement is already achieved. Thank you, thank you, thank you.